So basically in this video I wanted to do stoichiometry because I wanted to, look at these problems, kind of reflect back on this video for myself and also for you guys, just if you're trying to learn stoichiometry. And I'm going to go step by step, just trying to understand, trying to show you guys basically some of the basics of stoichiometry and maybe a little bit more advanced as we go. So let's get to it. So the first problem is, what is the empirical formula of a molecule containing 65% of carbon, 5.5% of hydrogen, and 29% of oxygen? So if we first divide this out, we have to do this by each percent. So 65 divided by 12.011, and note that's the molar mass of carbon. And if we get that, we get approximately 5.45. So first we do these numbers because we're going to figure out that these are like the portions of the molecules. So basically what we'll do is we'll look for the smallest number and we'll see how is it relation to the other two numbers. For example, it might be 3/2. One number might be 3/2 bigger than another number, and thus like one number will be 3, the other one will be 2 based on that molecule. So for carbon, it's going to be 3.5, and already going through the math, and if you decided to pause the video and do the math for yourself, you would also notice that hydrogen is 5.5, very close to carbon, so they're probably around the same. And oxygen is actually 1.8. So if you do the math here, you'll notice that if you multiply, you divide 5.5 divided by 1.8, you'll 5 divided by 5.5 divided by 1.8, you'll get a number very close to 3. So based on this, we can already tell that there are 3 atoms of carbon, 3 atoms of hydrogen, and 1 atom of oxygen. Thus, the empirical formula for this is going to be C3H3O. So that's the empirical formula for this. Now, using this guy right here, in the second problem, we say if the molar mass of the compound is 110 grams per mole, what is the molecular formula? So basically all we need to do now is we're going to take the percentage again. So what we're going to do is that we're going to so first let's keep C3H3O in mind. And so basically what we're going to do is we're going to multiply all of this out with the masses. So we'll have 3 times 12.011 plus 3 times 1.008 plus 16. Now if you notice here, that's 3 times the mass of carbon, and that's 3 times the mass of hydrogen. So basically what you're trying to see here, what we're trying to see here is we're trying to find the entire mass, and then we're going to divide it by then we're going to divide that number by 110 grams per mole, and then that's the number that we're going to multiply off our empirical formula to get the actual one, to get the molecular formula. So first we'll do this math. So 3 times 12.011 plus 3 times 1.008 plus 16. We get approximately 55. So we'll do 110 divided by 55. And the number that we get is 2. So if it's 2, therefore we have to multiply this formula by 2. And so basically instead of C3H3O, we're going to get C6H6O2. And that's basically how you do that kind of problem. Okay. So moving on, we're going to do a different kind of problem now. And this one is basically on balancing equations and identifying what kind are they, basically. So here we have this problem that says balance the equations and identify each of the reactions. So for this one, actually I can probably do this on pencil as well, or actually I'll still do it here. So first we'll write out, we have Na3PO4 plus KOH is NaOH plus K3PO4. So there's five kinds of reactions. One is double replacement, and where if you have two items, A and B, plus C and D, they end up they switch. So this guy will switch there, that guy will switch there. So basically whatever this one will eventually go to like AD and B plus BC is what the other side will be. The other one is single replacement, so instead of 2 and 2, it'll be 2 and 1. So basically these two will be together plus this one, and this guy will just switch out with one of them. And then there's synthesis, where it's just one thing plus another is equal to something. Decomposition, which is just one thing that turns into one thing plus another thing. And then finally combustion, which is a special case, and we'll get to it because it's actually one of the problems. So basically in this case, we can first we're trying to balance the equation, or actually we can first do the reaction type. So basically we see there's an Na, there's a PO, and there's a K, an O, and H. Here we see an Na and an OH plus a K3 and a PO4. So we can both see the PO4s, and we can see in this one it's connected to the Na, and this one is connected to the K. So therefore we know this one is a double replacement. And for this next one, and to balance out the equation, first we see that the NAs are okay. So we'll do, just to make them even, so there's 3 of them, so there's going to be 3 Na. So now we're going to put a 3 in front of there, so therefore this Na is also 3. But then now we have to realize that the oxygen is now 3, and the hydrogen is now 3. Let's ignore this for now and go to the K. And so for the K, we'll see there's 3 of the Ks, and there's 1 of the K here, so we'll put the 3 there. And now there's also a 3 of that and 3 of that. So let's add them up first. So we see there's 1 P on that side, there's 1 P on that side. We're good for that. 4 oxygen and 7 oxygen. 3 oxygen, 4 oxygen, there's 7. We're good there. Hydrogen, there's 3 there, there's 3 there. We're good. Na3, Na3. K, there's 3, K, there's 3. So we're basically good. And basically, normally you would put a 1, or you can just leave it blank in there. That'd be totally fine. So going on to the next one, we see CH4 plus O2 is carbon dioxide and water. So basically, if we look at this, it's a little bit, it's something a little bit weird, because you can see that at first you might think that, okay, so the hydrogen switches down to the oxygen, so therefore it should be single replacement. But then you notice that the oxygen splits up at this, so you might not actually have an idea. So this one's actually combustion, and for combustion you need to know that it's you usually have to identify an H2O and an O2. And most of the time there'll be carbon, so normally this is going to be your equation. Most of the time, with the exception of this CH4, that can be different at times. So let's go look at this, trying to balance. So the carbons they look good for now, so that we'll leave them there. But we can see the hydrogen, there's 4 there, and there's only 2 there. So we'll put a 2 in front of here. There we go. So 2 in there, so there's going to be 4 and 4. But then we notice that the oxygen is now 2. So there's going to be 4 of these. So 1, 2, 3, 4. There's 4 oxygen, so we need to put a 2 in front of there. Let's check everything as soon as we're done. There's 1 carbon, 1 carbon. That's good. 4 hydrogen, we're good. 4 oxygen, there's 2 oxygen, 2 oxygen, so therefore it's 4, so they're pretty good right there. Next, to go through this next one, we see that it's N2 plus H3 is NH3. This one is synthesis, because it's just one thing adding to another is equal to one just single molecule. And to solve this, first we see that the hydrogens are totally fine, but we notice the nitrogens are not, so we have to put a 2 there. But now that makes 6 hydrogens, and now the hydrogens aren't okay. So these are the things you need to notice whenever you're doing these kind of problems, that you can't stray away from doing what you need to do. You can't stray away from like thinking, okay, the hydrogens are okay, now I did the nitrogens, now I don't have to do anything else. You always have to go back and check. So since there's 6 there, the only thing you need to do is put a 2 there. And now they're even, there's 6 hydrogens, and there's 2 nitrogens on each. And to the last one, we have aluminum plus HCl is H2 plus AlCl3. Now this one we can tell is a single replacement, because first the Al is all alone and then it becomes with something else. Then the HCl, first the hydrogen isn't alone and now it's alone. So yeah, so this one is a single replacement. So first we see that the hydrogen here is 2, but that one's 1. So we'll go deal with that. And we didn't deal with the aluminums because they looked fine. But now there's a little problem because that says 3, but that one is 2. So therefore you have to put, it might be a little bit confusing because there's a 3 there, but then it makes it 2. So basically what you have to do here is you have to double up a little bit. So actually no, it would be better if we, or actually yeah, that's fine there. So basically we would have to put a 6 here. Yeah, so basically what we have to do is we have to put a 6 there. And then we notice here that, okay, so we can put a 2 there. So therefore the CLs are totally fine. But then you can see that the aluminum's not fine anymore, so you have to put a 2 there. It doesn't disturb anything, and then we leave the last hydrogen. We have to put a 3 in front of it, so now there's 6. So these kinds are a little tricky. You have to jumble through back and forth until you kind of get it. And then you have to make sure it's all simplified. So there's 2, 6, 3, and 2. You can't simplify it anymore, so it's pretty good. So next we go on to our third kind, and this one is just saying a common demonstration in general chemistry courses is a volcano reaction. When ammonium dichromate is heated, it decomposes into chromium 3 oxide, nitrogen gas, and water vapor. So basically what this kind of problem is asking is, okay, so what is the equation for this? So here we'll try writing out the equation. So basically we know that ammonium dichromate, and so if you do remember, ammonium is NH4, so we'll do dichromate 2O7 with ammonium, and that's going to be chromium 3 oxide, so it's going to be Cr2, but since it's 3, it's going to be O3 with nitrogen gas and water vapor, H2O. But then we notice because there's a 2 here, we also have to put a 2 here to make sure that they're all even. Because of the equation. And so basically you can see it's a decomposition here. But then you also notice that the hydrogens are not equal. So and also the oxygen. So a quick switch is just to put a 4 here. And after that, you're pretty much good. So you have your hydrogens are pretty good, your oxygens are good, your chromates are good. So basically in these kind of equations, they're probably asking you, okay, how are you going to do this problem? And basically, how are you going to balance out, and like basically what is the equation? So basically they'll probably give you this word problem and you're going to have to figure out what it is just based on looking at the formula. And that's why it's good to always remember the old nomenclature chapters to remember all the naming. So here's another one. So basically using an activity series, either write the product of each of the reactions or state NR, and basically NR is no reaction. This reaction won't occur. So basically let's start by explaining what a activity series is. So basically this is an activity series. It's a little hard to fit on the screen, but here, so you can see the activity of metals. And if you want to pause and kind of take a look at this, it's fine, but basically all you need to know is that the higher ones have the priority. So basically if potassium was in a molecule and it's added with lithium, as you can see lithium's on the top and potassium's just a little bit lower, then a reaction would occur where lithium would most likely replace potassium. But let's say if it's lithium starting in the beginning and carbon's all alone, it's added to it, there won't be a reaction because lithium is more reactive than potassium. So yeah, so basically those are basically those. And note that these guys basically don't do much. So yeah, so if you wanted to pause the video and try doing these for yourselves, you are more than welcome to. But here, let's go. So for this one, nickel and hydrogen and oxygen. Basically, nickel is more reactive than hydrogen. So basically, we know that there's going to be a reaction, and basically, the reaction is going to be NO, and this is going to be solid, and IO plus hydrogen, and because it's H2, we know it's a gas. Going on to this next one, we know that bromine is more reactive than iodine. So basically, then we will take, then it will be KBr plus I2. So iodine. So that's basically how you do those. Then for this next one, we know that, I believe that's cadmium. Cadmium is less reactive than hydrogen gas. So therefore, this will not react. There will be no reaction. And this one, nickel and AgNO3. Basically, this one, basically for this problem, we know that nickel is more reactive than silver because silver was one of the lower ones. So therefore, it's going to be Ag plus NiNO3. So basically, all you need to know is that once you figure out that there could be a reaction because one is higher than the other, you just switch them up. And here are some word problems that we can try doing. So this is going to be silver and sulfuric acid. Now, we know that silver is one of the bottom ones, so it's not going to react much. So it's just going to be no reaction. Then we have, finally, sodium and water. So basically how I like doing these problems is I like doing the actual one. So approximately it's going to be something like that. Or don't lead to it, but it's sodium and water. And basically we try taking the Na because it's more reactive than the hydrogen. And basically we're going to get this sodium hydroxide right here. So NaOH. And we just add it to some hydrogen gas. So basically, what you might be wondering is, okay, so why did the hydrogen split? Well, this is another form of combustion where it's H2O. I believe this is another form of combustion, and then that's why there's two hydrogens. I'm not 100% sure, but please do tell me if you do know if it is combustion or not. But yeah, that's basically it for these guys. And going on to the last one, this one is just talking about the real kind of stoichiometry. And this one's asking how many grams of calcium carbonate are required to prepare 50 grams of calcium oxide. And they give us this nice little formula. And what's nice about it is that it's already balanced, so we don't have to do much about that. But basically, we're going to have to do it in a little kind of table sort of fashion. So basically, it's mostly math from here. So we have our 50 grams of CaO, because we know that's of calcium oxide. And we're trying to find the calcium carbonate. So basically, we have this guy. And we're going to multiply that by... and basically, we need to find a conversion factor. So we first need to find the mass of the molar mass of calcium, and then the molar mass of oxygen. You add them together, and that's approximately 56 grams of CaO, and that converts to 1 mole. So this might not be very clear, but basically what you can do is take the grams of something. Once you know the grams of something, you convert it into moles of another thing, and basically if there's any coefficients, of course you multiply the moles out, but in this case we won't have to. Get the mole of CaO, 1 mole of CaO, and then you can convert it into another mole, 1 mole CaO, into 1 mole of CaCO3. And that way we can find the mass of CaCO3. This might be a little bit confusing, but after practicing a little bit, it does get a little bit easier. So yeah. Then what we can do here is, just like instead of turning it into something else, we'll try turning it from moles back into grams. So we'll multiply by 1 mole of CaCO2, and that's approximately, calcium carbonate. That's so we need the molar mass of calcium, molar mass of carbon, and the molar mass of CO3. The molar mass of O3. So basically, that's approximately 100. I think 100 point. Okay. Yeah. Okay. So 100.086 grams of that of CaCO3, and it's very important to label things so you know how I do them. And basically, we do our math, so we know these guys cancel out, these guys cancel out, and yeah, basically, now all you have to do is the math. So we know it's 50 divided, 50 times the 100.086. Then you divide it, divide that answer by the 56. And our answer is approximately 89.4 grams. 89.4 grams of CaCO3. And so that's basically how you do most of stoichiometry, and that's basically it for this video. I hope you did like it, and please tell me what you thought about it, and thank you for watching. I'll see you next time.